The next simulation I want to look at are the types of electromagnetic pulses that we might encounter. This could be problematic for electronic equipment. The first is lightning, but you can have very high current densities. And I'm using a model for a lightning pulse. This would be located, if we model a lightning pulse as a single column at ground level, z equals 0, is given by this current density here. Okay, this is from Cho and Lay. And tau is a characteristic time of like 5 microseconds. Q is 12, 16 coulombs. And we can model this using a time-dependent XY symmetry in QuickField. This is lightning. Okay. This is our geometry file, very simple geometry. The lightning bolt has a radius of 20 centimeters that I have here. Okay. These are block labels. This is the air region. We have a conductor next to it. We can see the current that's going to be induced in the conductor here. All right, this is our lightning region. And I've given it a unit permeability. Now, the current density using the parameters from the Lay article, then this is the formula that we can enter here. So it's t times an exponential of the square root of t, basically. Okay. And so the problem, we're in transient magnetics now, XY symmetry. So the lightning bolt is perpendicular to the page here. We'll solve it again. Okay. Now, the lightning pulse happens very quick. In fact, we're having to discrete, this is on the order of microseconds. So we're only simulating a very, very short interval of time. Calculating the solution at each time moment, and then we can look at a time plot for the field and induced currents in nearby conductors. Okay, now let's look at a time plot here. Just pick an arbitrary point. Okay. This is the potential. Okay. We can also look at the magnetic field. So that's the characteristic pulse here in terms of a t times an exponential. We can animate the solution. Now, this is the field here at 0.01 seconds. So we can look at the field at different positions in time, and it's a little bit denser there. So let's run the animation here. Okay. So this is it during the lightning strike as we're progressing in time. I can zoom in a little closer here to look at this. Let's look at the nearby conductor we have. We can see the current that's been induced in it. Okay. So I'll look at a time plot of this conductor. We'll look at the induced current, or the total current. It's calculating the integral at each time step. Okay, so this is the current that's been induced in roughly a 1 centimeter diameter conducting object here. So this is quite a substantial current that's been induced in this object. And notice the sign has changed, so the actual induced current's in opposite direction of the pulse. And we can shield this using different types of shielding as we've had before. We can also look at the Joule heating in the rod. The next type of pulse I want to look at, another type of electromagnetic pulse. This is due to airburst nuclear detonation. And the mechanism for that pulse, when you have a nuclear detonation in the upper atmosphere, notice you won't get the EMP pulse for a ground level detonation. The gamma rays are knocking off electrons from atoms in the upper atmosphere. There's Compton scattering. So you have a very large production of free electrons. And these free electrons are relativistic and they have a net downward velocity. And now they'll be perturbed by the Earth's magnetic field. And this will give rise to an electromagnetic pulse. And it depends on the yield of the weapon and also the altitude of detonation. It also depends on the inclination of the Earth's magnetic field. So different points of the Earth will give different EMPs for the same altitude. One test that was conducted near Hawaii, Starfish Prime, an upper atmosphere test, knocked out Honolulu lights in Honolulu from a distance of about 1,500 kilometers. There's also a test in former Soviet Union, Test 184, that had similar sort of damage. Although it was a smaller device, it was a lot closer to more types of electronics that could be interfered with. So with the different components of the pulse, we have a pulse component. It's 3 components, E1, E2, and E3. The E1 pulse lasts less than 1 microsecond, and that's due to electrons from gamma ionized atoms in the upper atmosphere, deviated by the Earth's magnetic field. And this pulse lasts about 200 nanoseconds. It's down by a factor of half after 200 nanoseconds. The E2 component results from scattered gamma rays produced by weapon neutrons roughly between 1 microsecond and 1 second. The E3 pulse results from a restoration of the Earth's magnetic field displaced by the nuclear blast. So the nuclear blast is going to heave the huge section of the Earth's magnetic field out of the way, and these field lines will then restore back to their original value. So we can simulate an E1 component using transient magnetics with a pulse with about 200 nanoseconds, and as well we'll simulate the E3 component. Okay. We can also look at some ways to shield against. All right. So this is the transient magnetics model, and it's an axial symmetric model. And I'm modeling, look at the different regions here. We have a copper region. It's the air, a copper cylinder. Actually, it's a ring. We're going to take the EMP to have a vertical direction. And I've assigned a vector potential flux function according to an impulse function. So here we have an impulse in time, and this is roughly 0.2 microseconds, or 200 nanoseconds. Okay, so this will give us our pulse. Let's look at the properties here. Look at our timing. So I'm calculating up to 1 microsecond with a step of 10 to the negative 8 seconds. And I'm storing the results at every 10 to the negative 8 seconds. Okay. And then our copper region, this is a cylinder, not a cylinder, but a ring, is as a square cross-section of 1 millimeter. So this is just representative of maybe some circuit element experiencing EMP, and this could cause shortages and so forth. Let's go ahead and solve it. Okay, it's already been solved, so we just look at the solution here. And I'll animate the solution. Okay. This is time t equals 0, and now we start to increase in time. The EMP pulse. We're also looking at field lines generated by the current in the object that's being affected by the EMP pulse. Animation is continuing. Okay, and then it's repeating, the animation repeated here. Okay, let's stop this and look at the object here. Okay, so this is the induced field in the object. And we can look at the total current density as well as the joule heating. Okay. We'll look at a time plot. All right, that's a flux function. Time plot curves. Now look at integral values. We can look at the total current, which is the same as the eddy current here. Okay, so it's actually calculating the integral value at each time step at this position here. Okay, let's close this. You can see it very much follows the EMP profile, the 200 picotesla pulse, and we reach a current about 6.5 amperes in this 1 square millimeter copper conductor. This could cause some problems in our electrical systems. So one way we can do this is put a ground plane or a conducting plane next to this and see if we can harden this a little bit. Okay. So this is the same problem. All I've done is inserted a 1 millimeter thickness copper plane next to our circuit element. So let's look at the solution here. Okay. And now we can zoom in. We can animate the solution. This is the initial EMP. We can also look at the current density as a function of time. These are just the flux lines, which are rather dense at this point. A little bit later in the pulse. Okay. I'll stop the animation here, and we can look at the current induced in the component at this point. Okay. Once again, we go to time plot. Okay. Integrals. And I'm going to go to the total current. Which is recalculating the current in the component we looked at previously. Okay. Well, the current's been reduced by about a factor of 5 in this here. So it's about 1 ampere of current. So we can introduce nearby conductors and things to reduce the current that's going to exist in some of our more sensitive electronic components so they don't get fried. Okay. The next thing I want to look at is the E3 component of the EMP, which is due to the restoration of the Earth's magnetic field after the blast. Okay. This is the E3 component. Okay. Once again, I'm looking at a circular conductor. This is an axial symmetric problem. Make it a little bigger here. Okay. Let's look at the properties. Transient magnetics, axisymmetry. Okay. Once again, I have a cable. The cable has a diameter of 1 centimeter and a radius of 300 meters. So the slow component of the EMP is going to be more problematic for very long conductors because the Earth's magnetic field, roughly 50 microtesla, but it's changing, and it can result in very large currents being established in long conductors and power lines and so forth, and result in transformer failure and various things that aren't good. It's a vertically directed pulse. Okay. Now the vector potential on the side, the flux function, I'm given it this function here, which is 1 minus e to the minus t over 100. Now this is going to be in seconds. And this will give us, this vector function will give us roughly 50 microtesla when the Earth's magnetic field is restored. So I just chose this to give us 50 microtesla when after roughly 200 seconds. Okay. Let's look at the solution, or maybe solve it. Let's see here. It's not a very big problem. Notice I don't have a very fine mesh density here. We really need a finer mesh density where our conductor is going to be. So I've simulated up to 200 seconds of this pulse. Okay. And this is what the flux function looks like. I'm going to go ahead and zoom into our cable. Once again, it's 1 centimeter diameter, and the solution region is 300 meters roughly. Okay, there it is. Okay. And I'm going to look at the current flowing in this. Okay, so this is, once again, we'll look at a time plot. Okay. Integral values. And we'll look at the total current, which is the same as the eddy current, as a function of time. Okay. This is in amperes. It reaches about 1 ampere, or actually 1/2 ampere, and then it kind of dies off as the Earth's magnetic field is going back into its normal configuration here. So if we have very long, this is 300 meter cable, so if we're going to very larger cables, the surge could be even greater here, and it could be quite substantial as far as damage. Okay, so that's about all the applications that I was going to show today. I think we might have gone a couple minutes over. And if you want to see some more examples, you can visit jblearning.com and see applied electromagnetics using QuickField and MATLAB, as well as see some of our previous webinars.